This lab was broken into two parts. The first part involved finding the mass of an unknown black hole given information about the trajectory of a star that orbits the black hole and its related quantities. Part 2 involved estimating the required initial velocity for a spacecraft that was taking off from a planet that orbits the black hole, the same black hole from Part 1, in the same direction of motion as the planet. The purpose of this experiment was to explore three main things. The first one is curving motion, the momentum principle, and the force of gravity. The model for Part 1 depicts a randomly generated trajectory of a star orbiting a black hole. Notice here the mass of the black hole, the average of those values, the Fnet parallel component, and the perpendicular components. For Part 2, this model depicts a trajectory of a spacecraft that was launched from a planet orbiting a black hole in the same direction of the planet's motion. So the pink line represents the spacecraft's direction of motion, and the cyan path represents the planet's orbit. As a preview, we found that the black hole mass was 1.836 times 10 to the power 36, and the spaceship's velocity was 2 times 10 to the power 8 in the negative x direction, and 1 times 10 to the power of 6 in the positive y direction. The main physics principles involved were the curving motion, which helped us break down Fnet into its parallel and perpendicular components. This also broke down further using the momentum principle, which is dp over dt. We can break down the parallel components. These two equations are especially important because we have a relatively easy formula for the parallel component, and we can find the perpendicular component by subtracting Fnet minus the parallel component. We also have the momentum principle, which helped us find that the momentum was equal to Fnet times the change in time. We also have the force of gravity, and the formula is right here. I made three assumptions about initial conditions. The first assumption was that there was no other forces other than ones mentioned in the instructions. We also assumed that the spaceship cannot travel more than the speed of light, and we treated systems in this experiment as point masses, even though they had radiuses. There were multiple combinations of systems and surroundings depending on what value we're trying to find. So depending on the value we're trying to find, some of them would be the system, some would be surrounding. In Part 1, the system would be the black hole, and the system would be the planet, the star. The system would be the star, and the surroundings would be the black hole's effect. In the Part 2, it would be, the main thing would be, the system would be the spaceship, and the surroundings would be the black hole, planet, and star. And for all scenarios, the overall surrounding was space. The initial conditions for Part 1 was that we had the planet's trajectory and related values such as direction and velocity, the mass of a star, and we needed to find the mass of the black hole. In Part 2, we had the masses of the planet, ship, star, and black hole, and related components of the trajectory of the planet and star. We also had the ship's initial launch direction, and we needed to find the ship's initial launch magnitude velocity. Coding. For coding, I will go back here. Using the scaffolding, I implemented the three main principles we were trying to explore, which is the curving motion, the force of gravity, and the momentum principle. I'm going to scroll to let you guys see that. That's for Part 2. And for Part 1, there you go. Okay, and then the similarities and differences. Well, this was a purely coding experiment, so we didn't have anything to compare it to. For the what if questions, the difference between the parallel and the perpendicular components of the change in momentum versus the Fnet parallel components is that Fnet is change in momentum over change in time, whereas the change in momentum is just the overall change, the absolute change. For the what does it mean question, I couldn't really figure it out, but my thought process was that we needed to get into a correct distance from the gravity that allows the inertia to help the momentum, not for the momentum and the parallel and perpendicular components of momentum to balance out so that it does not get sucked into the black hole while also not being shot out of the black hole.